All right, let's get started here. This is our last live lecture. And I just want to let you know, well, of course, I mentioned this last time, that ideally you come in to the on-campus final, do it on Tuesday if you must. Monday's acceptable, but it might be a little crowded in there. Plenty of room on the Tuesday final. And let's see here. And over here today, I just got week 10 up here. So this sort of thing I'll be going over. And what I think you'll appreciate is having some practice final questions. And this will kind of give you an idea of what the written in class final is like. And of course, the take-home portion will be much like exam 2 was, but just covering everything over the whole term. And that's where you can, of course, refer to the lecture notes, and so you know how to do it. But as always, think of the take-home portion as you're showing me what you could do to do a really impressive report covering the data, that you can incorporate the impressive, professional-looking graphics, going through all the steps, and then supporting it with the output from StatCrunch. Let's see here. We don't need this up there anymore. Don't think we need this. Hey, let's go take a look at this checklist number 10. You probably haven't seen it, I just got it posted today. In fact, you probably weren't even aware of week 10 being up there yet. Let's take a look at it. All right, so the idea is you got this entire week to review for the final. Now, here's what I recommend as I got this in this checklist. Now, most of you have already gotten your stats toolbox done, but here's what I'm suggesting. Even though you've done everything, here's some things you may not have included in there, but you might consider including them because it's going to really help you for the final. So here's what I recommend. Now, you'll probably say, well, why didn't you tell me this at the beginning? Well, I came up with this after further reflection. As I was looking at some of the ones being turned in, I didn't think they'd be as helpful as they would be if these things were included. Now, the number one thing, and of course you can go into the online textbook. I'm going back here to the chapter contents, and of course you can go to these chapters and look through the exercises there and see if perhaps you could find one that's particularly intriguing to you. Now let's suppose I'm over here, chapter 11. How about, well, that's 2 population proportions. I was thinking, okay, so this is goodness of fit test. And I'm going to go in here. Actually went to the following chapter, but that's so that way I can just back up. And it's a nice, quick, easy way to get to the exercises. Whoops. Okay, it's going to cooperate. I was afraid it was going to have to wait for some Adobe to download. That would take longer. Actually, I should have had this fired up ahead of time. But the idea is you're trying to find a nice concrete example, something that's memorable to you. So here I am. I'm going, oh, let me just go back a page. Okay, so let's suppose, well, one of the methods is the chi-square goodness of fit test. Is there one in here that looks particularly interesting to you? Now, for me, something I found really interesting is Benford's law, because this is how you're able to catch embezzlers who are cooking the books, and they have no idea, most people don't, that the last digit in a number, you think it'd be equally likely it's any one of them. turns out it's not. It's almost bizarre that's the case, but we actually know what actually happens when you have data gathered. Who knew? But you can use that to test to see if what they actually had in their cooked books matches with Benford's law. And you'd be using the chi-square goodness of fit test to try it out. And so, if it's interesting to you, maybe not. So find something else that is. But that's the idea. So let's suppose I'm trying to remember now, what's the deal with the chi-square goodness of fit test? Well, I come up with a classic example. I say, well, what sets it apart from all the others? Well, the idea is the data following the claimed distribution. Now, the claimed distribution is what Benford's law says it should be. And so the null hypothesis is that there's no difference between my data and Benford's law. In other words, it's following the claimed distribution. And the alternative says, oh, no, it doesn't. And of course, they're in trouble if it doesn't, because it looks very suspicious. But I got a concrete example that makes it easier for me to remember what it is about it that helps me recognize that method. And then I run through my head what the null and alternative hypothesis would look like. And I got a concrete example to help me with that. And then what are the conditions that need to be met? And I run that through my head, random sample, all the expected values are 1 or more, and no more than 20% of the expected values are less than 5. And you might make a note to yourself, and of course I won't know that till I let StatCrunch calculate the expected values for me. Oh, and then you say, now, is there a second choice for the chi-square goodness of fit test? And hopefully you'll say, well, no. In fact, it appears that whenever we have categorical data, there's no second choice. I don't know if you've noticed that or not, but that's the way it is. And the reason is that categorical data needs much larger sample sizes in order to get things narrowed down. So quite often what happens is with categorical data, your sample size is big enough to meet the conditions, but once you look at your results, you realize things haven't gotten narrowed down enough. And the idea is, hey, if your sample size isn't even big enough to meet the conditions, just forget about it, because things are not going to be narrowed down enough. It's what we call, it lacks the accuracy we need to get our answers to our interesting questions. But when we have the quantitative numerical data, then it's worth having a second choice, because maybe things will be narrowed down enough, even though we have a small sample size. Not necessarily, but it could be. It all depends on the situation. But at least you got a second choice there. Now, continuing on down, you might say that, is there anything I could follow up with? Well, with the chi-square goodness of fit test, you can look at the chi-square contribution and see which categories it was most off from, if that's interesting to you. But that's all you really got with the chi-square goodness of fit test. I mean, there's no confidence intervals or anything like that. All right? So do that. So have this little list. Now let's just run through it again. Because what you'd like to do, because you got nothing else to do this week, nothing else, and this is what you could be doing, so that after doing this for about a week, you'll find that you can actually look at a situation and you know which statistical method to use. Now, to help you with this, let's go over here and let's get, let me go back to the main menu here. And learning modules, and module 10, there's this which statistical method to use. Let's take a look at that. Oh, well, not that one. Oh, I guess that's right, it's the Word document. So right here, this describes the question you ask yourself to know which experiment to do. So for each one of these, you might include this in there. So like here, the goodness of fit. I make a note that, okay, it's this categorical or qualitative data. You just got one random sample. And what's unique about it, that sets it apart from everything else, is someone is claiming they know what proportion of the population is in these multiple categories, 3 or more categories. They know what percentage of the population in each one. And we want to test that claim. So that's different from any of the others. And if there's anything else you want to add to that, well, in essence, you're checking to see how good the fit is between your random sample and what the claim distribution is. Because you expect your random sample to be reasonably close, not exact, but reasonably close, the sort of thing you'd expect to see if the null hypothesis were true, which is there's no difference between your random sample and the claim distribution. But this is your little guide for the telltale signs that tell you which statistical method to use. And so this is what you want to keep reviewing, that you want a nice perfect application for each one of these. Now notice that for this one, population mean, that once you come with that application, then of course you can follow it up with the second choice, and that you review what those non-parametric methods were that you were covering earlier. And that's kind of what you're going to get practice with these practice final questions. In fact, we'll take a look at those as soon as I run through this list here. Oh, now, and I guess I should have mentioned that you don't really need to come up with any data or anything here. I mean, just doing these things will help you immensely. Show what the null alternative hypotheses for that method. Is there anything you can follow up with? If so, what is it? And then state, well, now, both situations, if my p-value was less my significance level, what would my conclusion be? And state it in context. Don't just say this, but rather, what would be the conclusion in the context of this particular statistical method? For example, if it was a one-way Anova, you'd say that, oh, if my p-value is that small, then I would conclude that at least one of the population means are different. And you would add that to find out which ones are different, I would use a Tukey test to do that. So that's the big context, the application, how you'd be using what you learned in this class to get the information you want from your data. And then, of course, state what you would do if the p-value was larger than the significance level. In a one-way ANOVA, you'd say, nope, doesn't appear to be any difference between our populations. And of course, this right here, I was talking about earlier, state the questions you ask yourself. And of course, to help you with that is this document right here that's available to you right here, which statistical method to use. Also, the stats binder topics. Let's see, do I have that one already open? Let's see. Here it is. So here's the list of all of them that you got. And so just make sure you got application. Now, the last ones are pretty easy because these match up with the second choices here. In other words, one sample sign test, that's what you follow with. The population mean for one population. So let's go ahead and take a look at this practice final questions. Now, I'm not going to give away the answers because you're going to be able to check those out, but I just kind of want to clarify what's it going to be like. And let's see, where did I open that yet? Oh, I guess I better get that open. I thought I had it open. I'll just open it this way. Oh, it's going to be that way. Oh, there we go. All right. Now, what I want you to notice is with this on the last page, you've got the screenshot instructions. So you don't think you have to remember the name of these things. Okay? That you can look up. Oh yeah, that's what the stat crunch function is called. So just realize you've got that at your disposal. But here's the sort of thing you'll see, because you don't need a calculator, and you got this little screenshot instructions to refer to as you're doing all of this. So we have two dependent random samples. These differences are a small sample and is not normally distributed. We want to know if the medians are different. Oh, okay. So I'm not going to say too much here, but you just, of course, this is why you want to practice writing out your hypotheses. Oh, and for medians, just don't do a capital letter M, okay? Because for some people, their capital letter M looks just like a mu. You can't tell them apart. So if it's a median, write out the word median, and then I won't be scratching my head wondering what you were actually saying. And which StatCrunch function would you use to get the p-value? And of course, you just go over here to your screenshot instructions and look that up. And then, of course, now let's suppose, just like you practiced with your little stats binder, you say, oh, well, now if my p-value here is less than this, what's my conclusion? Okay. So this is all the stuff that you've been running through your head, hopefully each day, this whole week on each of these statistical methods. And if you're thinking, all those statistical methods, that's way too many. Well, it's not that bad, keeping in mind that these 5 overlap with these. That these, if these are really on your stats tool belt, these are the tools you know, well, then you should be able to recognize where they go. Otherwise, you really haven't learned it yet. And likewise, and notice this next one, they're giving you this. And hopefully what will pop into your head is your special example of that you've been reviewing. And so it's very clear to you what the hypotheses are. And so on, filling that out. Then your parametric, which is just another name for your first choice method. Non-parametric is your second choice. And here they're giving you the scenario here. But anyway, so you'll be able to check this all out. But this way, it gives you an idea of what to expect. They just have 5 here, but that's enough to give you an idea and hopefully get you to appreciate how helpful it would be if you followed that advice and came up with those practice applications that are meaningful to you. So let's see now. Where do I have everything? Get that out of the way. All right, so we got that, we got that. Yeah, right here. And so you did come up with good applications, not just, this I'll do, I don't know. But the better they are, the more pleasant it is, or it shouldn't be unpleasant as you run them through your head each day. And of course, what you'll find is it keeps getting easier each day as you do it. So that's the nice thing. So in case you're wondering, aren't we going to learn more statistical methods? Well, I thought it'd be great to have this week to really get them to sink in so that the ones you do know, you know really, really well. And so let's try this just to see how you're doing. I'm going to, I'll move this over here. And let's put this over here. So this way you got the nice list to look at. And without me saying too much, I'm going to take a look at an assortment here. Some possible ones. So let's just take a look at, say, this one right here. So let's suppose an introductory statistics instructor believes now they said median, but what I would say is the center, because I would have this rephrase, because I'm not going to lead you and tell you what to use for the center. You'll have to figure it out. So, but because I got this from the textbook, I just copied and put it in here, but I want you to know, I would say believes that the center or typical number of hours a student study each week is less than 15. He randomly sampled 20 students, asked them to disclose the number of hours they study each week, and here's the data. Now, what I would ask, like what you see right here, they set the median, but do we necessarily want to use the median? You need to address whether or not we can use our first choice, the parametric method. And if the conditions are met, then that's what you're going to do, is test it, see if it's the population mean is less than 15. But if the conditions are not met, you're going to test to see if the population median is less than 15. And of course, so this is why it's so helpful for you to know how to check the conditions. And now for this one, if the conditions were met, it would be the population mean for one population. But if the conditions were not met, that's the sign test. Let me also get my little, I might switch over here too. So let's go over here. I'll switch back and forth between this and the other one. But you'll see that, all right, so it would be the t-stats, one sample, and of course that's enough because it could either be data, or in this case would be data, but the main thing, t-stats, one sample. Then of course the conditions are not met, we'd be over here the non-parametrics, and you could just say sign test, just like it says here. So this is why we have this. You can just say it the way it says it here. You see, but over here, Larry, you said one sample sign test. Well, you can just say sign test. Whatever you have StatCrunch calling it is fine. All right. So then, of course, you would go ahead and carry it out. Now, of course, we're talking about the take-home portion where you'd actually be doing the work. So what I showed you earlier was what the written part would look like. Okay, but this gives you an idea, because this is what you got to do in real life. Do I get to my first choice, or do I have to use my second choice? Because the sample size is less than 20. And let's take a look at another one. So I'm covering this in very general terms. He said, but aren't you actually going to do it? Look, we've done that already. Now, if you're rusty and not feeling up to par with that, then all you need to do is go back to the learning modules and go back to when you were working on that, so forth. Now, it is true that at first you were just using your calculator for these, but I'm hoping that when you were doing the non-parametric methods, that you were reviewing how to also use StatCrunch instead. Because then you get the pretty output, which your calculator doesn't give you. So let's get back. Yeah, we'll leave that there. And I'll have this up here. Okay, let's see what else is next. Let's see what's going on here. So the Insurance Institute for Highway Safety conducts experiments in which cars are crashed into a fixed barrier at 40 miles per hour. Well, that's expensive. Do you think we can afford to have large sample sizes? I don't think so. So we're going to be stuck with small sample sizes because of the nature of this experiment. And so what we're doing here is we're measuring the femur force here on the left leg resulting from this crash. And so we're looking at these measurements for large family cars. So we're considering what it is for the population of all large family cars, considering what it would be for the population of all passenger vans, and the population of all mid-sized utility vehicles. Of course, we don't have the data for the whole population, because if we did, all the cars would be crashed. Now, that's no good. So we got to have a sample. So we got these samples from these 3 different populations. Now, so essentially we want to know, is this amount of femur force, is it the same for all 3 populations? Or is it different for at least one? Now, so with that being the case, hopefully, maybe looking over here, you'd have an idea of what that statistical method would be and what the first choice is. And because it's quantitative data, it's probably a second choice. And do you know what it is? And then, of course, once you realize, you'll do everything testing to see if the conditions are met for the first choice. Hopefully by now you recognize it's a one-way ANOVA. And there were 4 conditions, weren't there? Let's see. So all 3 of these would need to be random samples. And let's see now. I'm reading this carefully now for the 2 biggest things. Now, it didn't actually say they were random samples, so we'd have to demand to know, now, were these randomly sampled ones, or did you cherry pick them, huh? What did you do? So we'd want to verify that. Now, they're independent because they're obviously not matched or paired up in any way, so we have the independent samples. Then you want to know if the populations are normal, so you would do that, that normality test we have. As you recall, we were using that a lot back here. Let's go on back. There. Oh, I need to get over here to the website. There we go. Let's go over here. Remember a Kruskal-Wallis test? Because we were always having to check for the first choice, which was one-way ANOVA. And if it didn't work out, like on the example we're looking at, it was the Kruskal-Wallis test. Now, when I was going over this with you on the live lecture, yes, it shows the probability plots and the box plot, but that normality test was far more reliable. Let's see, did I show that here? But when you ran the first choice, you're able to do that normality test, as I was showing you in the live lecture 2 weeks ago. And that's a little more reliable. And the reason is, so I'm used to doing the, in my lecture class, these, what we call them probability plots. StatCrunch calls them QQ plots. But the problem with these is, unlike Minitab, these don't have the boundary lines, because Minitab not only has the boundary lines, but it also gives a p-value, just like the Wilks test that StatCrunch has. So for StatCrunch, instead of doing this, it's better to do that normality test that you can run when you're checking for the first choice conditions. And you'd be doing that for each one of these. It's more reliable because it's too hard to read the QQ plots in StatCrunch. It's one kind of a weak area if I compare it with Minitab, but it makes up for it entirely if you use the that Wilks test to check for normality. Now let's get over here. Is it there? No. All right, so what did I just do? Oh, I know what it was. That's one I want to get back up. Now, going back over here. All right, so once again, first choice is one-way Anova. And hopefully you recognize that we're looking at quantitative numerical data from 3 or more populations. Hopefully you've got your own special application. And you know the 4 conditions. Oh, I mentioned the 3, but I didn't get to the 4th one, which is equal population variances. So you'll calculate the sample standard deviation from each one of these. And if the biggest sample standard deviation isn't more than double the smallest, then we can say equal population variances. So if all those 4 conditions were met, well, of course, we're going to have to just fudge on the normal populations. We'll say, okay, excuse me, random samples, then the conditions will all be met. And if one of those fail, well, if random sample fails, you're dead in the water. But if the normal populations or equal population variances fail, then you can do the Kruskal-Wallis test. Okay, so let's take a look at another one here. Now let's suppose we're wondering, can I use one variable to predict the other? Now it depends what you'd want to do. Probably, chances are, you could hear the crickets chirping and you might wonder if I could use those to predict what the temperature is because you don't have a temperature gauge with you. Is it possible to do that? Well, you want to know, well, I could if there was a correlation between these. So I guess the question is there a correlation or an association between these 2 quantitative numerical variables? So it's important to note that they're quantitative numerical data, and you're wondering if they're correlated or associated with each other. And ideally, you'd realize what that is. Let's go take a look here. Looking at your little list, you're going, that sounds to me like inference for linear regression. And you're right. Now, of course, ideally, you've got your special example, and that you know the null hypothesis is that there's no correlation. And we're talking first choice here. And the alternative is that there is a correlation. And of course, if there is, what would you follow it up with? Well, confidence and prediction intervals. And these are for where you're saying, okay, let's suppose my X variable that I'm using to predict the Y variable, let's suppose my X variable is equal to this. And if that being the case, I could plug that in and a prediction interval would be telling me for one individual from that population what I would predict for that one individual for that particular X value. Whereas a confidence interval says, okay, now from the entire population, this would be the average of all the Y variables from that population for that given X value. So that's the difference between the 2. You hopefully got your concrete example to help keep that straight in your mind. Now, this is if the conditions are met. So this is what you keep reviewing with your classic example. So, what were those conditions again? Well, we got to have a random sample, of course. The other is that the residuals have to be normally distributed. And then that it has constant error variance by looking at the residual plot and see if there's constant error variance or homoscedasticity, if you want to be fancy, with no discernible pattern. Now, if it doesn't meet all those conditions, what's this? Is there a second choice? And you're saying yes, Spearman's rank correlation test. So that would be your second choice if you don't meet the first conditions on this one. All right, let's go take a look at another one. This is an interesting application. Maybe this would be your classic example if you found it interesting. So we got this pit boss. He's concerned that this pair of dice being used is not fair. Something's fishy about them. Well, from probability theory, we know what the expected distribution is when you roll a pair of dice. Because when you have the sum of a pair of dice, they're not all equally likely. In other words, there's more ways to get a sum of 7 than there is for the old snake eyes or boxcars. So the claim distribution is that if you roll the dice a large number of times, that would be our random sample, then you expect it to be reasonably close to what probability theory says it is. So that would be our claim distribution, that the dice are fair. So if you roll the dice a bunch of times and it matches this pretty closely, well, the null hypothesis says there's no difference between your dice and what the probability theory says it is. The dice are fair. But if it strays too far from this, that would be evidence supporting the alternative, that it's not following this claim distribution, and therefore the dice are loaded. And boy, that'll make the pit boss angry. So pit boss rolls dice 400 times, and here's the number of times, the counts, or all the frequencies that they occur. Now, how would you determine how well this data fits this claim distribution? How good would that fit be? Now, what would be the name of that? Goodness of fit test. So this is a very interesting application. I don't think as good as Benford's, but maybe you like this one better. But this goodness of fit test has some interesting applications. It's just a matter of you finding one you find interesting. So, all right, goodness of fit test. Is there a second choice? No, there is not. Okay. What you'd have to do is you just got to roll the dice a large number of times in order to get things narrowed down enough. Now, the conditions that need to be met. Well, the nice thing is the chi-squares, it's all the same. So you learn these conditions, it's good for the 3 chi-squares. So random sample, all expected values, at least 1, and no more than 20% of expected values less than 5. And of course, you'll get the expected values after you've run StatCrunch. And of course, over here in StatCrunch, let's see, now that was where you went to tables, and then there was, let me see here. Contingency, frequency. Oh yeah, excuse me, over here, stat. And then there was goodness of fit and chi-square. There it is. Took me a while to remember. I haven't done that in StatCrunch for a while. It's different in Minitab. Minitab, you actually do go to a table first and that. And that's why I got screenshot instructions in case I confused myself going from one software package to the other. That's why I don't expect you to memorize this, because maybe after this class, you'll be using a completely different software package. But that's okay. The idea is that you recognize which statistical method you need, and then you'll just have to look it up, whatever software package you're using, and they're all going to give you the p-value that you need. And you'll be able to know which hypothesis to go with. And of course, they'll also have the follow-up things. Now, for goodness of fit, all you're really going to see is the chi-square contribution, so you can see which ones were categories was my actual counts really far off from. So you can see the suspicious areas. Yeah, you can see which sums the dice were loaded for. Maybe the ones that would have the biggest payout. And that's what the pit boss is looking for. Oh, let's look at this one. The General Social Survey regularly asks individuals to disclose their religious affiliation. The following data represent the religious affiliation of young adults, 18 and 19, in these different decades, 70s through the 2000s, double odds. Does the data suggest different proportions of these 18 and 29-year-olds have been affiliated with religion in the past 4 decades? So we want to know if the population proportion in each of these 4 groups or 4 different populations, are all the population proportions equal to each other, or is at least one of them different? So that's what it's asking for. And if you're looking over here, that test for homogeneity of population proportions, also known as test for equal population proportions, whichever you want to call it. But so then you know that the null hypothesis, think of it, it looks like the categorical version of a one-way ANOVA, doesn't it? The null is all the population proportions are equal to each other. The alternative is that at least one population proportion is different. But no, you don't do a one-way ANOVA on it because this is not quantitative numerical data. What you got to do here for this one is you realize that what you actually do is the chi-square test on it. And that p-value will let you know whether it's reasonable to believe the population proportions have at least one that is different. Of course, that's what you'd conclude with if your p-value is smaller in your significance level. But if it's bigger, then you'll say, nah, I don't seem to see a difference between my population proportions. Let's look at this one. Okay, we're looking at oil changes. The following data represent the cost of an oil change in dollars in 3 different geographic regions for 2 types of service centers. A specialty chain is an oil change facility that specializes in oil changes, while a general service station provides a wide array of services in addition to oil changes. So we've got location, which has 3 categories in it, and service center, which has 2 categories in it. But notice that for where this category and this category overlap, there's 3 quantitative measurements. So what this is a random sample of 3 taken from a Chicago location specialty chain. And like this one right here. Oh, this is a random sample of 3 from the Bolingbrook location from a general service center. So we got 1, 2, 3, 4, 5, 6 cubby holes, but each cubby hole has a random sample of quantitative data. So here's another way of looking at it. Because we're looking at these costs, and you might be asking yourself, I wonder if location plays a factor in the cost, or is the cost the same for all of these 3 different levels? And we also wonder, I wonder if the service type of service center it is plays a factor in the cost. That is it the same for both of these, or is it different? All right, so if you want to know if this plays a factor and this plays a factor, you're looking at 2 different factors, aren't you? And that makes it a 2-way ANOVA. And how you recognize it is that you got a table, but each cubbyhole doesn't have a single number like a chi-square test of independence, but it has a random sample in each cubbyhole. So 2-way ANOVA, and let's run through our heads. This one could you really need a good example for this one because you got more to run through your head on this one than any of the others. This is the most involved one of them all. So first thing you ask yourself is, okay now, first I test to see if there's an interaction effect between location and service center. And so you'll do that hypothesis test first. And if there's no interaction, then you'll go ahead and test for the main effects, which just another way of saying do a 1-way ANOVA for location, and then do a 1-way ANOVA for the service center. And of course, if you do find that at least one of these is different, then you'd follow up with a Tukey test to see which of these 3 levels is different. And then, of course, if you see a difference between these 2, do a Tukey test and see if they're different. Okay. Well, actually, when there's only 2, it kind of simplifies things down, doesn't it? Because you only got 2. So it's really more interesting if you've got 3 or more, like here. 2, it just becomes a little too simple. Because if you go with the alternative hypothesis, you know they're different. Because it's when you have 3 or more that you need the Tukey test to figure out which are different, which are the same. All right. And then, and let's not forget checking conditions. But if you know how to check conditions for a one-way ANOVA, you know how to check conditions for a two-way ANOVA. The same 4 things. Oh, let's see. Oh, this last one. So if any of you do have any questions, do let me know. Oh, wait, there is a question. I didn't see that. I'm sorry. Is there a source to check answers to problems from the book? Yes, because it has answers in the back. Here, let's go over there and take a look. Sheet down here, there's the answers. They got answers to odd number ones. So it's just like a regular textbook where you got answers in the back. So yes, and sorry, I didn't, you probably asked that a long time ago. Usually my thing will beep and let me know someone has asked a question, but if it did, I missed it. So please, if you come up with any more questions, I'll try to stay a little more on top of it because we're getting near the end here. Let's see. In many colleges and universities around the country, educators are changing their approach to instruction from a teacher lecture-centered model to a student-centered model, where students learn in a laboratory environment in which students can proceed at a pace suitable to their learning needs, and lecture is de-emphasized. In one school where this model is being introduced, of the 743 students who are enrolled in the traditional lecture model, 364 passed. So we had 364 successes out of 743 trials. Then in the student center model, got a sample of 567, and we had 335 successes out of the 567 trials. Now, does the evidence suggest that the student center model results in a higher pass rate than traditional? Okay. And so, of course, the null hypothesis, how much of a difference does the null say there is? Null, none, no difference between them. And the alternative says, oh, yes, there is. And which inequality is the one they're asking about? So you'll want to know if the population proportion for the student-centered model, that population proportion is bigger than it is for the traditional model. And who would be able to figure that out? And hopefully you realize, well, we got 2 populations we're comparing with each other, and it's this categorical or qualitative data. So we're comparing population proportions for 2 populations. And is there a second choice? Well, this is categorical or qualitative data. So the answer is, look, if your sample size isn't big enough, well, then just forget about it. But it is. You can look at these sample sizes, and they're quite large. You have that little test, n times p times 1 minus p. And when I say p, I mean p hat. Those are all at least 10. But let's do it the easy way. That you basically have 4 piles here. From the first sample, you have 364 in one pile, and the other pile you'll have, well, 743 minus 364. Well, that's way bigger than 10. Over here, in one pile, you have 335 in that pile, and the other pile, you'll have this number minus that one. You don't need to subtract it. You can know that's way bigger than 10. So yeah, your sample sizes are big enough, and what may not be clear is it a random sample? Well, to make this a controlled experiment, what you would really have to do is randomly assign students to 2 groups, and they're all thinking they're going to all be taught the same way. It's just that the ones get assigned to one group are taught in the traditional model, and the ones who got randomly assigned to the other group are in the student-centered model. That would be a controlled experiment. And you wouldn't necessarily tell them you're doing experiments, so they're staying blind to the effect. So that would make it a controlled experiment and would be appropriate. But if the students knew ahead of time how it's being done and they just picked it accordingly, well, no, that there'd be confounding factors then. Okay, well, hopefully that gives you a better idea. And I do encourage you to give it a try. Try to come up with your great best applications you can come up with. And if you include these things, I'm hoping you're seeing how much they'll help you, particularly in the written exam, because these are all the things that you're going to be wanting to know as you're taking it. And, the better your examples are and the more you review, the easier the test will be for you. But better yet, you'll actually learn and know after the class is over how to identify the correct statistical method, which is really the whole goal of the course. Okay, so let me see. Any other questions? Not seeing any. So, okay, so that's it for this week, and hopefully those methods will get easier and easier for you to remember.